Shall I start? Okay, thank you. Yeah, good morning, friends. Welcome back to our session, GATE session. We have been dealing with calculus. A part of it is an important aspect of calculus is vector calculus, a calculus in vectorial sense. So vector calculus for a BTech student, it is a nightmare when he is doing his BTech course, because they think that it is difficult to do problems in this topic. But this is very important, my dear friends. For example, if you take mechanical engineering, if you have fluid flows, you have thermal conductivity and aerodynamics, everywhere you use vector calculus. So similarly in civil engineering, you have strength of materials, you have stress forces, strains, and then strength of materials. Everywhere you use this vector calculus. And ECE student, without vector calculus, they cannot do anything, because they have spatial coordinate system, signals and systems, then electromagnetic theory. Electromagnetic theory is equally important for electrical engineering students also, in which they deal with Maxwell's field equations and which involves completely vector calculus. So today I will start vector calculus. Just I alarm you, it's a hectic schedule today, hectic activity today. We have a lot of stuff to deliver. We have complete vector calculus, and then around 80 to 90 problems today we will do we'll discuss during this session today. So pull up our thoughts, please. Right. So vector calculus, in all the examples I have mentioned till now, on fluid dynamics, civil engineering, maybe mechanical engineering, electronics, electrical, the purpose of vector calculus is to study the motion of a particle in space. That is the most important thing. Is the main application of vector functions is the analysis of motion in space. Either it is a movement of a particle on which a force is applied, or maybe fluid flow, thermal conductivity, anything. It is the analysis of motion in space. So in these two basic important things we have to understand very clearly here. We use these two words very frequently. One is scalar function and scalar field. Other one is vector function and vector field. Let us see what we mean by this scalar function and scalar vector function. A scalar function of a scalar variable t is a function f of t which uniquely associates a scalar f of t for every value of t in a given interval ab. So if you take any t, any point in an interval ab, at that point, if you can define a scalar function, most of the students, and in fact some teachers also, get confused. What is the difference between scalar function and constant? Scalar function is not a constant. Scalar function is a function of time, but does not have a vectorial, does not have a direction. It's not a vector, but it's a function of t, or maybe x, y, z spatial coordinates, or time coordinate t. So in a given interval of t, for each t, if you can assign a scalar quantity f of t, then such a function is called scalar point function. Scalar field. So the domain on which f of t is defined, that is called a scalar field. It is a region in space such that for every point p in that region, a scalar function f of p is defined. Say for example, once again, if I take a metal body or as a solid rod, something like this, the best example for a scalar function, if I start heating this body from this end, gradually the temperature is the function here, energy is gradually dissipates through the body, it spreads throughout the body, okay, and after some time the whole body has some temperature, may not be uniform temperature. So at this point I have some temperature, at this point I have some other temperature, at this point I have some other temperature, at this point I have some other temperature. So the temperature of the body changes with the location of the point I am considering. If I take here one point, another point, another point, another point, and at each and every point of this body, the temperature, which is a scalar quantity, is defined. So this is my scalar field, and my temperature energy function is the scalar function. It depends with spatial coordinates sometimes say for example it is fully heated up and then pull off the source, remove the source, then gradually what happens? The temperature gradually comes down. Then it changes with time. So f of t here, if time t represents time or spatial coordinates x, y, z, whatever it is, if you can define a scalar throughout the given field or the domain of the function, then it is called a scalar. The best example is temperature of the body. Then vector function. A similar way, vector function of a scalar variable t is a function f of t which uniquely associates a vector f for each t. Similar sense, if you can define a vector function at each value of t, then it is called a vector point function, and such a region in space is called a vector field. Then, because we have done enough of vector analysis, vector algebra in +2 level, you have seen what is a vector, magnitude of a vector, and then position vectors, and then addition of vectors, multiplication of vectors, cross product, dot product, the angle between the vector, so many things, components of vector along x-axis, y-axis, z-axis are I, j, k, normal vector. You have done so many things. Now we are not going into the analysis or algebra of vectors. Our topic is vector calculus. As I said earlier in calculus is the study of the behavior of the dependent variable with respect to the independent variable. When I say vector point function f bar of t, t is the independent variable and f bar depends on t. Now we study how this f bar changes with the independent variable. That's what is all about vector calculus. The first idea is derivative, vector derivative. Let f bar u be a vector point function. Then derivative of f bar u with respect to u is defined as df by du is equal to limit h tends to 0 f of u plus h minus f bar of u by h. The definition is very much similar to your ordinary derivative dy by dx. And if f bar u is equal to f1 u plus f2 u plus f3, mind you, this f1, f2 or f3 are scalar functions. Okay, and when you multiply these things with I, j, k respectively and add them, then it gives a vector. Then df by du is equal to df1 by du I, df2 by du j, df3 by du k. This is what we call vector derivative. So in basic results, df by du of f bar plus g plus or minus g is equal to df by du plus or minus d by, if f bar is a constant then it becomes 0. d by du of f of u f bar u is equal to df by du f bar plus alpha into df bar by du. Then d by du of f bar dot g bar dot product df by du. See, just like uv product, it comes like a uv product only. df by du dot g plus f dot dg by du. Then cross product also it follows a uv property df by du cross g plus f cross dg by du, just like derivative of u into v by the similar way. But mind you, in dot product, even if you don't mention the order, there is no loss here. But in cross product, you have to maintain the order. You cannot change the order. F comes first, g comes next. Here also on the right hand side, the derivative of f comes first, df by du cross g plus f cross dg by du. Because if you change the order in cross product, there will be a change of sign. We know that a cross b is equal to minus b cross a. Then d by du of f cross g cross h is equal to f cross g bar g cross dh by du plus f cross dg by du cross h plus df by du cross. Similar thing, f, g, h, the same order should be maintained throughout. Okay. If r bar t represents the position vector of p in space and t is the time independent variable, then general expression is x bar is equal to general expression for the position vector is r bar is equal to x of t I bar plus y of t j bar plus z of t k bar. Then dr by d represents the velocity and d square r by dt square represents acceleration. As I said, vector calculus talks about the motion in space, analysis of a motion of a particle in space. If r is the position of a point in the space, then the particle changes with time, just like it moves from one point to another point with respect to time. So that change is given by x of t I plus y of t j plus z of t k. With time, this position of the particle changes. That's why it's called position vector. Then dr by dt change, that is called velocity, and d square by dt square is called acceleration. So some more basic things. If a bar is equal to a1i plus a2j plus a3k, b bar is equal to b1i plus b2j plus b3k are two vectors. You need these properties to find the angle between surfaces and then other things. So just I'm recapping these definitions one so that you will get accustomed to use it to these definitions. Then a dot b is mod a mod b cos theta, where theta is the angle between the two vectors. In problems, we need the formula very importantly. You may be asked to find the angle between two surfaces. Then theta is equal to a dot b by mod a mod b. Cos inverse of that gives you the angle between two vectors. Similarly, a dot b is a1i plus a2j plus a3k dot b1i plus b2j plus b3k gives you a1 b1 plus a2 b2 plus a3 b3. And a dot b is a scalar product. That means the output is always a scalar quantity. Similarly, a cross b is mod a mod b n sin theta, where theta is the angle between the two vectors and n is the normal vector to both these vectors. That means if a bar and b bar and xy plane, let us say like this is a bar, this b bar, and then if you consider a cross b, then a cross b will be in the direction which is normal to both this a and b. This is a, this is b, this vector must be normal to both a and b. So n bar is a normal vector to both the vectors. That means your n bar will be, if a, b are in xy plane, this n bar will be along z axis, parallel to z axis. And this a cross b is given by I, j, k, a1, a2, a3, b1, b2, b3, where a1, a2, a3, b1, b2, b3 are components of a and b, vectors a and b along I, j and k. Then a cross b is defined. Like this is also very important definition for us in vector differential operators. We will be dealing with so many problems involving these four properties. So it should be very much fluent with these four properties. Example 1. Find magnitude of the velocity and acceleration at t is equal to 0 of a particle moving along. X is equal to e power minus t, y is equal to 2 cos 3t, z is equal to 2 sin 3t. So this is the what is given is the particle is given you, position of the particle is given to you. What is the position? X is equal to e power minus t, y is equal to 2 cos 3t and z is equal to 2 sin 3t. As I said earlier, this R bar is a standard definition. Remember this throughout our discussion. R bar is xti plus ytj plus zk or xi plus yj plus zk. So here in the position vector, x, y and z are given to you in the problem. So your R bar is e power minus t I, 2 cos 3t j, 2 sin 3t k. So velocity, you are asked to find the velocity. Velocity is dr by dt. So dx by dt I, dy by dt j plus dz by dt k. So derivative of e power minus t minus e power minus t, 2 cos 3t is minus 6 sin 3t j plus 6 cos 3t k. So this is velocity vector. What is required? Velocity at t is equal to 0. If you put t is equal to 0, this will be minus I, this will be 0 and this is 6. What next? The magnitude of velocity. First we have to calculate velocity and then find the magnitude of velocity. Magnitude of a1i plus b1j plus c1k, the magnitude is a1 square plus b1 square plus c1 square whole power 1 by 2. So 1 plus 36 under root 2, that is root 37. And if you want to calculate acceleration, again differentiate the velocity function. So dv by dt. So d square x by dt square I, d square y by dt square j, d square z by dt square k. So again this becomes derivative of this is e power minus I minus 18 cos 3t minus 18 sin 3t k. Yet if you t is equal to 0, if you want the acceleration, put t is equal to 0, the sign terms become 0. So this will be 1 I minus 18j and the magnitude of the acceleration is square root of 325. This type of problems we are getting in the GATE examination. So if a bar is a constant, we have standard result. Then it may be like asked like this: if a bar is a constant vector, then which one of the following is true? A cross dA by dt is equal to 0. A dot dA by dt is equal to 0. Okay, a square is mod a square is equal to 0, something like this. So you need to know standard result. This is a standard result. So a bar dot a bar is a square. We know that. If you differentiate now with respect to t, as I using the previous property, a bar dot dA by dt plus dA by dt dot a bar, because a dot b is equal to b dot a, we get twice a bar dot dA by dt is equal to 0. That means the dot product is 0. That means a bar dot dA by dt is 0. When the dot product is 0, we have one more principle that one of the magnitude of these two vectors must be equal to 0, or the angle between these two vectors must be 0. A dot b is equal to 0 means cos theta is equal to 0. If a bar and b are not null vectors, mod a not equal to b, mod a not equal to 0, mod b not equal to 0, then theta must be 90 degrees. So that here cos theta becomes 90, so a dot b becomes 0. So next problem. The position vector of a particle at time is r is equal to cos t minus 1i plus sin h t minus 1j plus alpha t cube k. Find the condition imposed on alpha by requiring that at time t is equal to 1, the acceleration is normal to the position vector. See, in vector calculus, what I observed is I have gone through so many great question papers. I'm giving some problems also from great in this presentation. Problems are directly formula substituted orientation problem, or they are involving logic. In most of the problems, they are using content and logic. So be very careful. The position vector of a particle at time is given. Find the condition to be imposed on alpha by requiring that at time t is equal to 1, the acceleration is normal to the position vector. So first you have to find the acceleration. So for that, first find the velocity. By differentiating this r bar once, we get minus sin t minus 1i plus cos h t minus 1j plus 3 alpha t square, that is velocity. Then acceleration is d square by dt square. We again differentiate minus cos t minus 1i plus sin h t minus 1j plus 6 alpha t. I'm sorry, this is 6 alpha t. So minus alpha plus 6 alpha k at t is equal to 1. So this is what we get. At r is equal to 1 I plus alpha k at t is equal to 1. What is required is the acceleration must be normal to the position vector. So this is position vector at t is equal to 1, and this is the acceleration at t is equal to 1. So dot product is 0. So minus alpha plus 6 alpha k dot I plus alpha k gives minus 1 plus 6 alpha square is equal to 0, or alpha is equal to 1 by square root of 6. This type of logic you have to sometimes use. So we need so many things here. You have to understand what the velocity, the acceleration, and normal vectors, concept of normality. And then this is the question given in gate 19. Vector b is obtained by rotating a vector a is equal to I plus j by 90 degrees about k, where I, j, k are unit vectors along x, y and z axis respectively. And then what is b bar? This is absolutely common, the understanding of the problem. Must have a clear understanding about I, j, k and rotation. Say we have x axis, y axis, I, j. Here I have taken a vector like this. Okay. This is my first quadrant. Let us say this is the first quadrant, this is second quadrant. I have taken a vector like this. And this vector is rotated by 90 degrees. This point is given by I plus j, or the position vector is 1, 1. Everything is positive. This is rotated by 90 degrees. Now, where is this vector now? In the second quadrant. In the second quadrant, what happens? This is negative x-axis and positive like this. Rotate 90 degrees. This is negative x-axis and positive y-axis. So, the same point, magnitude is same. So, what happens? Component along x-axis becomes negative 1, and y-axis becomes remains the same. So the remaining vector is minus I plus j. You need to understand the geometry of the I, j, k and position vector of a point for this. It needs clear understanding of the concept. So most of the problems here is conceptual based. Another question, gate 2020. So most of the slides I have taken from Day-4 with due credits, and thanks to Day-4 I have taken some questions from this thing. I have scanned some questions from that. This is from Day-20 problem. For three vectors A is equal to 2j minus 3k, B is equal to minus 2a plus k, C is equal to I minus j, where I, j, k are unit vectors along the axis of a right-handed rectangular Cartesian coordinate system. That's what we mean basically. What is the value of A dot B cross C plus 6? This is a very, very basic problem. Just dot products and cross products. So A, B, C are given to you. So A dot B cross C is also known as triple product. So that is given by the determinant of the components involved in that. 0, 2, 3. The components of A are 0, 2, 3. One more warning I am giving you while doing problems. See, for example, look at A, 2j minus 3k. While writing the determinant, what you do is first element is 2, add 2 immediately. But not so. The coefficient of j is 2. That means coefficient of I is 0. The common silly mistake that we generally do. 0i plus 2j. So the component of I is 0. But in a hurry, what the mistake we do is first we write 2. Okay, be very careful, be cool and do it. So component along I is 0, 2 minus 3. Here minus 2, 0, 1, 3 minus 1, 0. If you find this triple product ABC is this thing 0. So A dot B cross C plus 6, that is the required result is 6. It's a very simple problem that is given in Gate 2020. So find the angle between directions of velocity and acceleration vectors at t of a particle whose position vector is a similar problem. Here I have calculated the angle between acceleration and the position vector. So the principle that we use is A dot B is equal to mod A mod B cos theta, or theta is equal to cos inverse A dot B by A bar dot B bar. Based on the principle, we have to do this. Find the velocity, find the acceleration, and find the angle between these two vectors. So A bar is equal to t square I minus tj plus 2t plus 1k. B bar is equal to 2t minus 3i j minus ck. Find d by dt of A dot B, d by dt of magnitude of A plus B. For this, the first one is product rule. For the second one, we add A and B, then take the magnitude of A plus B, then take the derivative of this. Okay. And then get 17 bit is a question given in 2017. If a vector V has components 1, 2, 3, then its magnitude. Very simple question. So vector is Vxi plus Vyj plus Vzk. So magnitude is given by square root of 1 square plus 2 square plus 3 square. Right answer up to 2 decimal places. So square root of 1 plus 4 plus 9. That comes around root 14. Root 14, it comes around maybe 3.7 to 3. Between 3.7 to 3.79. So that is a question asked in 2017. Another question 2017. There are so many questions you can get from vector calculus. Be very careful. For a steady flow, the velocity field is V is equal to minus x square plus 3y plus 2xyz. The magnitude of the acceleration of a particle at 1, 1. By what he is asking acceleration. So first derivative with respect to this, first derivative or second derivative, put the point 1 minus 1 and take the magnitude. Then till now we have differentiated a vector point function or scalar point function at a point. So the vector coefficient d by dx or d by dt is also sometimes a vector operator. D by dt, earlier problems, it's a scalar operator. Now what happens if this differential operator is also a vector operator? Then that is called a del operator. It is given by I dou by dou x, j dou by dou y, k dou by dou z. So the del can be operated on scalar because the vector operator, it can be operated both on a scalar and vector point functions. in three different ways, because we have two types of products, dot product and cross products of vectors, and depending on the dot product and cross product, this del can be operated on vectors in two different ways and scalar on one way. These three are the trinity of vector calculus. The whole vector calculus and engineering applications are they completely based on the trinity. These three things, very, very, very important. And one is del f. Here f is a scalar point function. Then del f is called gradient of f. Gradient of f. Because del is a vector operator, what happens if f is a vector? If in the first case f is a scalar. If here f bar I take, then this is a vector, f bar is a vector. You can have two types of product, dot product and cross product. First dot product, del dot f bar is called divergence of f bar. It is a vector, sorry, f bar is a vector function, yes. And f bar is a vector function and del dot f bar is a scalar. Why? Dot product is also called as scalar product, the output is scalar. And what happens in the first case? F is a scalar function, del is vector operator, so del f becomes gradient and this becomes a vector. The second one, f bar is a vector but divergence is a scalar point function. So f bar is a vector, third one is f bar is a vector, then del cross f bar is called curl of the vector and is a vector point function. So after the three results we have, the first one is a scalar, first one is a vector, second one is a scalar, third one is a vector again. Let us see one by one. Gradient. If f of x by z be a scalar function, then del f is called, because del is I dou by dou x, j dou by dou y, k dou by dou z. Del f is called I dou f by dou x, j dou f by dou y plus k dou f by dou z. This is called gradient of the scalar function f. F is a scalar function, then grade f is given by I dou f by dou x, j dou f by dou y plus k dou f by dou z. So basically what does this f of x, y, z represent? So let us say f of x, y, z, a scalar function, generally in vector calculus it represents a surface in the space. A surface, like I take a surface of this rice, this is a surface. So in x, y, z plane I take a surface like this and the value of the surface, and as x, y, z, the location of the point that I select changes, this f of x, y, z is defined at different points and it defines a surface. Then if f of x, y, z is a surface, then what does this grade f represent? Then grade f is along normal to the surface, f of x, y, z is equal to constant. That means if you want to say, if you want to find the normal to the surface at any point of the surface like this is surface. If you want to find normal to the surface like this, then that is given by gradient of the scalar point function which defines the surface. Angle between any two surfaces, basing on this principle, because del f gives gradient of, gives the normal to the surface, angle between any two surfaces f of x, y, z is equal to c1, g of x, y, z is equal to c2. The angle between the normal c is the angle between surface. Say for example, I take a surface like this, I take another surface like this. What is the angle between the two surfaces? The angle between the two surfaces is nothing but the angle between the normal, tangents to the surfaces. Angle between the tangents to the surfaces, or else angles between the normals to the surface. Okay, so normals are obtained by grade f and grade g. So the angle between these two things gives the angle between the two surfaces. Another thing is directional derivative is one more important application of this gradient. The directional derivative of f of x, y, z, the given surface at a p is a dot product, a component of dou f in the direction of unit vector of b bar. It is denoted by df by ds bar. So till now we are finding the derivative of a vectorial derivative of vector point function or a scalar derivative, right? So if you want to find the derivative and the components of the derivative along some other direction, some other vector, so that is what we call by directional derivative. It is obtained by df by ds is equal to grade f dot b bar. B bar is the direction in which we want to find the directional derivative. B bar is the, see, the dot product of df by in the direction of the unit vector of b bar. We want to find the directional derivative along b bar. That is our b. We do a couple of problems to understand in a better way. At I and j, this is given GATE 2007, I and j unit vectors in the xy directions respectively for the function f of xy is equal to x cubed plus y square. The gradient of the function is given by, what is the gradient? Gradient is given by I dou f by dou x plus j dou f by dou y plus k dou f by dou z, but the given vector is given only in the xy plane. So what happens? K component, this last term becomes 0. So then I dou f by dou x is 3x square plus j dou f by dou y, that is 2y. So answer is 3x square I plus 2yz. That is our gradient to the function. Find the directional derivative of f of xyz is equal to 4 e power 2x minus y plus z at 1, 1, minus 1 in the direction towards the point minus 3, 5, 6. See, I said directional derivative along b. That's what I said. But the b is not directly given here. What is the direction of b? Find the directional derivative of this at 1, 1, minus 1 in the direction towards the point minus 3, 5, 6. So b is directed along the vector joining this point and this point. So first thing what you have to do is, first is grade f. What is grade f? I dou by dou x, j dou by dou y plus k dou by dou z of the scalar value, scalar function. So that is, this is what we get. I into dou by dou x is e power 2x into 2. So that's how this grade f vector comes out. And then grade f at this point 1, 1, minus 1, to substitute 1, 1, minus 1 here, e power 2 minus 1 minus 1. So what is what we get here? 2 minus 1 and minus 1 e power 0, that is 4 e power 2i minus j plus k. So this is grade f. And then we need to calculate n bar now, b bar now. B bar is vector connecting 1, 1, minus 1 and minus 3, 5, 6. So that is given by minus 3 minus 1, 5 minus 1, 6 minus of minus 1, minus 4i plus 4j plus 7k. And what exactly b bar by mod b bar? So mod b bar is, or mod a bar is minus 4i plus 4j plus 7k by square root of 16 plus 16 plus 49, magnitude of the vector dividing by magnitude of the vector gives you the normal vector. So minus 4i plus 4j plus 7 by 81, that comes out to be 9. So directional derivative now is grade f dot b bar by magnitude of b. So grade f is 4 into 2i minus j plus k dot a cap. So this is what we have, minus 20 by 9. This gives the directional derivative. Find the constants a and b so that the surface ax square minus byz plus is equal to a plus 2 into x will be orthogonal to 4x square y plus z cube is equal to 4. So we have to find a and b such that these two surfaces are normal. So when the surfaces are normal, what do you mean by that? Their normals are perpendicular to each other. So find the normal to this one, find the normal to this one, and show that when two vectors are perpendicular, what happens? A dot b becomes 0. That's exactly what we do. So what are the normals to this? This normal is given by gradient. This is also given by gradient. So gradient of f at 1 minus 1 2 is I into dou f by dou x 2ax minus a minus 2 minus dou f by dou j. Dou f by dou y means minus bz minus dou f by dou z minus by k. And you have to consider this at point 1 minus 1 2. So the vector is a minus 2i minus 2bj plus bk. This is the vector normal to the first surface. Similarly, find the normal to the second surface. Gradient of z, this is g. Dou f by dou x 8xy I. Dou f by dou y 4x square j. Dou f by dou z 3z square k at the given point 1 minus 1 2. So comes out to be minus 8I plus 4j plus 12k. So I want these two normals to be perpendicular to one another because I want the normals to be orthogonal. Orthogonal means perpendicular to each other. So del f dot del g is equal to dot product is to minus 8 into a minus 2 plus 4 into minus 2b 8b plus 12 into b 12b. So this is what we get. If you simplify this, we get 2a minus b is equal to 4. Still we cannot find a and b directly. We need some more relation because a and b are two arbitrary, two constants here you have to evaluate, and we have one more equation. Only one equation. One more equation is required. So since this 1 minus 1 2 is common to both, this point is common to both the point. That's why we are able to find normal at 1 minus 1 2. So because this point is on this surface, you substitute here, what we get, a plus 2b is equal to a plus 2. Or else if you simplify this, b is equal to 1. And if you put this b is equal to 1 in the first equation, you get a is equal to 5 by 2. So the values of a and b are a is equal to 5 by 2 and b is equal to 1. This you have to use some logic here, right? Show that. This is they don't ask you in the examination show that, but they can ask a question like this. If f of r is a function of scalar function of r, where r bar is xi plus yj plus zk, then what is gradient of f of r is equal to, some options may be given to you. Since r is equal to xi plus yj plus zk, we have r square is the magnitude square is x square plus y square plus z square. If you differentiate this with respect to x, 2r into dou r by dou x is equal to, on the right hand side, if you differentiate with respect to x, we get 2x. So dou r by dou x is x by r, dou r by dou y is y by r, dou r by dou z is z by r. So whenever r is equal to xi plus yj plus zk, we have dou r by dou x is x by r, dou r by dou y is y by r, dou r by dou z is z by r. It's a standard result. Standard result, this may be even directly asked as a question. If r is a position vector of a point, what is dou r by dou x? Okay. So this is a standard result, you have to remember this. So gradient of del fr now is I dou by dou x plus j dou by dou y plus k dou by dou z of f bar. I write this sigma notation I f dash r into dou r by dou x, because derivative of f with respect to r into dou r by dou x, j into f dash r dou r by dou y plus k into f dash r dou r by dou z. This is what we mean by this summation operator. F dash r is there, but dou r by dou x is x by r. So this is f dash r by r sigma ix bar ix, this is f dash r by sigma x means ix plus jy plus zk, that is r bar. This is what we required. Find the directional derivative of the function xy square plus yz square plus zx square along the tangent to the curve x is equal to t, y is equal to t square, z is equal to t cube at the point 1 minus 1 1. If these problems they never give you directly, they put some condition here. In the earlier problem, vector joining 2 points, here directional derivative along the tangent to some other curve surface. Be very clear, okay? Read the problem very clearly. So first grade f dot normal vector we want, unit vector we want. So grade f is I dou f by dou x plus j dou f by dou y k dou f by dou z. So this is, if you differentiate this with respect, this is what we get. Grade f at 1 1 1 is so and so. And then position vector or the position of any point on this curve is given by x is equal to t, y is equal to t square, z is equal to t cube. And the position vector is given by xi plus yj plus zk or ti plus t square j plus t cube k. So tangent is given by tangent dr by dt is always along the tangent. We have discussed, right? We have been studying this right from 10th class. The tangent is along the derivative will be, the derivative of a function gives you the tangential direction. Gradient of scalar gives you normal direction. We hope you understand the difference between these two. Derivative of the position vector gives the tangential direction. Gradient of the surface gives you normal direction. So now, I'm sorry. dr by dt, what is required is tangent is now dr by t is vector along tangent to the curve. So dr by t is I plus 2tj plus 3t square. At point this is I plus 2j plus 3k. So the normal vector in this direction, tangential direction, is I plus 2j plus 3k by square root of plus 1 plus 4 plus 9, that is square root of 14. So the direction, the vector, unit vector is given to you, grade f is given to you. Now you have to find the directional derivative, that is given by grade f dot this unit vector, this square root of I plus 2j plus 3k dot is I plus this thing. That gives you the directional derivative. Evaluate the angle between the normals to the surface xy is equal to z square at the points 4, 1, 2 and 3, 3, minus 3. Two normals are given to surface is like this. One normal is like this at this point. Another normal is like this at this point. Okay. So what is the angle between this normal and this normal? They meet somewhere here and you have to find the angle between these two. So dou f by dou x, normals are given by in general grade f. So dou f by dou x is y, dou f by dou y is x, and dou f by dou z is minus 2z. So grade f is normal at any point is yi plus xj plus minus 2zk. So you want to have a normal at this point and another normal at this point. First find the normals, two normals. At 412, grade f at 412 is, if you put this 412, I plus 4j minus 4k. Similarly, grade f at 3, 3 minus 3, 3i, 3j minus 6k. Okay, plus 6k. Plus 6k. So cos theta is a dot b by mod a mod to mod b. That is the principle we have for theta. So the magnitude of this vector is square root of 1 plus 16 plus 16. This is square root of 9 plus 9 plus 36. So this is denominator is square root of 33 into 54, and the dot product of the two vectors is 1 into 3 plus 4 into 3 minus 4 into 6. This is what we get. This is how we get the angle between these two normals to the surface at two different points. Yes, the temperature of a point here, this is the example I have started actually. Temperature is the energy function. It always gives a scalar defined by a scalar point function. Temperature at a point xyz is given by T of xyz is equal to x square plus y square minus z. A mosquito located at 112 desires to fly in such a direction that it will get warm as soon as possible. In what direction it should be? The direction along the maximum direction is along the normal direction. So along grade phi. The greatest rate of increase of t at any point is given by gradient t in direction. So gradient of t is I dou t by dou x, j dou t by dou y plus k dou t by dz, where t is x square plus y square minus z. So gradient is I into 2x plus j into 2y k into minus 1 2xi plus 2ij minus k. At the given point 1, 1, 2, 2i plus 2j minus k. So the mosquito must fly in the direction of 2i plus 2j minus k to get warm as soon as possible. The temperature dissipation of temperature will be maximum along the normal to the surface. That is the principle. If a bar is a constant vector, then prove that gradient of a dot bar r bar is equal to a bar. A bar is, let us say, a1i plus a2j plus a3k, where a1, a2, a3 are constants, not functions of x, y, z. They are not functions of x, y and z. Okay. Then a dot bar r bar is a1i plus a2j plus a3k dot xi plus yj plus zk. So that comes out to be a1x plus a2y plus a3k, a3z. Okay. Then what is the gradient of a dot r? That's what we want. So dou f, this is, if you call this as f of x, y, z, I into dou f by dou x. What is dou f by dou x? a1, a1i plus j dou f by dou y. Dou f by dou y is a2. dou f by dou z is a3. So gradient of a bar dot r is I dou f by dou x, j dou f by dou y plus k dou f by dou z, that is a1i plus a2j plus a3k, the given vector a. The problem, they don't ask you to prove if a is a constant vector given by a1i plus a2j plus a3k, then gradient of a dot bar r dot is a is r. Option 1 is a bar, option B is r bar, option C is 0, option D is none of the above, something else. Then we have to do this and put the answer, correct answer. And a question from gate 19. If x, y and z are directions in Cartesian coordinate systems and I, j, k are the respective unit vectors, the directional derivative of the function u of x, y, z is equal to x square minus 3yz at the point 2, 0, minus 4 in the direction of I plus j minus k, 2k divided by square root of 6 is, what is that? Directional derivative. See, because surface is given, first we have to find the gradient normal to the surface, gradient u. Okay. In the direction what we want this is already unit vector. Why? Because I plus j minus 2k, the magnitude is square root of 1 plus 1 plus 4. 1 plus 1 plus 4 is 6. Square root of 6 by square root of 6, 1. So it's already unit vector. So you need not find. So grade u dot this vector. First you have to find grade u dot this vector. Grade u at this point 2, 0, minus 4 dot this vector gives you the directional derivative. So very frequently and every year without a break we are getting a guarantee question from directional derivative. So keep that in mind and practice more problems on directional derivative. This is also given in 2019 and as a directional derivative, I suppose. A scalar function is given by f of x, y equal to x square plus y square. Take I bar and j bar unit vectors along x axis and y axis respectively. At xy is equal to 3, 4, the direction along which f increases the fastest. Yes, this is also again related to gradient. Just now a few minutes back I told you the principle. What is the direction? It may be a standard question. What is the direction along which the surface f of x, y, z is increases in the fastest rate? At the fastest rate, the options A along the normal, B along the tangent, C along the internal inward normal, along D any other plane, any other vector. So gradient is always gives outward normal. Okay, the answer is along the gradient vector or along normal to the surface. That is the direction in which f changes at the fastest rate. This already we have done a problem on this. A fly problem. The temperature. How in what is the direction in which it gets temperature fast quickly. Similar problem here. Okay. First for that you have to find the gradient of this at the point 3, 4. That's all. That's enough. Just 1 minute problem. So 2xi plus 2yj, that is gradient. If you put 3, 4, the point 6i plus 8j. Okay. And then gate 18. In gate 18 also there is a question on directional derivative. The value of the directional derivative of the function phi of x, y, z is equal to x y square plus y z plus z square at the point 2 minus 1, 1 in the direction of the vector I plus 2j plus 2k. Again a problem on directional derivative. First grade phi, find grade phi, that is 2xy plus 2zx I, dou f by dou y is 2xy plus z square j plus 2yz plus x square k. Find the grade phi at the point 2 minus 1, 1. Okay. Dot the unit vector along this direction. So the gradient at this point dot the unit vector along this is I plus 2j plus 2k by square root of 1 plus 4 plus 4, 9, that is 3. So the grade phi at this point dot I plus 2j plus 2k by 3, that gives you the answer. Then gate 18. Here also another problem again gradient. So for a position vector r is equal to xi plus yj plus zk, the norm of the vector can be defined as R bar is equal to x square plus y square plus z square. Given function is f is equal to ln r. What is the gradient? Just few minutes back I told you what is the gradient. Question may be asked, not show that. So like this. But I have given the problem here. This is the problem I asked earlier. Okay. These type of problems that we are getting in the examinations. So be very prepared. Few minutes back I told you, we'll ask you like this. Given function is phi is equal to ln of r. Ln of r is where ln of mod r. Mod r is square root of x square plus y square plus z square. And log of this is log square root of x square plus y square plus z square. You can write as 1 by 2 ln x square plus y square plus z square. So if you use a derivative, then you get this answer C. And then exercise problems, I have given some vectors. Find the unit normal vector to this thing. Unit normal vector means first we have to find normal, that is gradient at the point. Then unit vector. Find the directional derivative of f in the direction of 2i minus j minus 2k. Find the directional derivative means again you have to find gradient here for this function at this point. Dot unit vector in this direction. That gives you directional derivative. Find the maximal directional derivative. That will be along the normal. Find the angle between the surfaces x square plus y square plus z square is equal to 9 and z is equal to x square plus y square minus 3 at 2 minus 1 2. Angle between the surfaces is nothing but angle between the tangents or angle between the normals to the surfaces. So for this surface, find normal. Normal means grade phi at 2 minus 1 2. Similarly, for this surface also find the normal at this point 2 minus 1 2. So you have two normals here. Surface is like this, you have one normal like this, you have one more normal like this. Then find cos theta between these two vectors. That is what is required here. If r is equal to xi plus yz plus zk and r is equal to modulus of r bar, then find gradient r and gradient of r power n. These are the standard problems you can. The last one is standard results. You can directly ask also in the examination what is gradient of r, where r is magnitude of r bar, or gradient of r power n. These are standard problems. Okay. Then comes divergence. So we have defined three types of products here. F is a scalar point function, then grade f gives gradient, then f is a vector point function, then divergence is del dot f bar dot product. That means scalar product. So output is a scalar quantity. Okay. If f bar of x bar z is a vector point function, then the divergence of f bar is defined by del dot f bar. So if f is f1i plus f2 plus f3k, then del dot f is I dou f by dou x, j dou f by dou y plus k dou f by dou z dot f1i plus f2j plus f3k. This is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. I'm sorry, this I is not be there. This is a mistake here. This is simply dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. And then whenever this del dot f bar becomes 0, this is a mistake here. I, j, k are not there here. Okay. I will correct it and put the PPT, upload the PPT. Don't worry. Okay, I correct it and I'll upload the PPT. Whenever the dot product this becomes 0, then f is called a solenoidal function. Solenoidal function. So some problems on this. Find divergence of f, where f is equal to gradient of this. F is a gradient of this, and then find divergence. Let this surface be phi x cube plus y cube plus z cube minus 3xyz. Then find the gradient of this is dou f by dou x I plus dou f by dou y j plus dou f by dou z k. So 3x square, dou f by dou x is 3x square minus 3yz, dou f by dou y 3y square minus 3zx, dou f by dou z 3z square minus 3xy. So grade phi is like this. This is what we get. Then for this I want divergence. So divergence is given by dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Again get the three derivatives and write this sum 6 into x plus y plus z. find B such that bx plus 4y square z plus y square z I x cube sin z minus 3y j minus e power x plus 4 cos x square y k is solenoidal. Solenoidal means del dot f is 0, then f is called solenoidal. So find del dot f, this is the vector here. Find del dot f here, because it is given as solenoidal, equal to 0, del dot f is equal to 0. Find the value of b. Let bx, the vector be f. So del dot f bar is I dou f by dou y, dou x, j dou f by dou y plus k dou f by dou z dot the given vector. So I into dou by dou x is dou f1 by dou x is b, dou f2 by dou y is minus 3, dou f3 by dou z, there is no z term here, derivative is 0, so we get b minus 3 equal to 0. Because since it is given a solenoidal function, del dot f must be equal to 0, implies b is equal to 3. The problem may be, if this vector is a solenoidal function, the value of b, 1, 2, 3, 4, find the correct value. Divergence of the vector field, u bar is equal to e power x into cos y I plus sin y j. Divergent is del dot u, that means dou f1 by dou x plus dou f2 by dou y. This is what you have to do. Dou f1 by dou x is e power x cos y, dou f2 by dou y is e power x cos y. So e power x cos y plus e power x cos y, 2 e power x cos y, this is what we get. C. Again another problem in 2017. The divergence of the vector minus yi plus xj is dou f1 by dou x, there is no x term here, 0. Dou f2 by dou y, no y term here, 0. Then the third type of product is del cross f. Del dot f is finished, divergence is finished. Now, in divergence, I want to tell, particularly for the civil and mechanical engineering student, they must have studied fluid mechanics in our BTech level. You study for incompressible fluids, you study the equation of continuity. Equation of continuity for incompressibility is del dot v is equal to 0. That is a very important application of divergence in fluid mechanics. Is if f bar represents the velocity function in 3 dimensions and the fluid is incompressible, then the equation of continuity is del dot f is equal to 0. Divergence of the velocity point function is 0. That gives you the equation of continuity. Then curl. Then del cross f. The curl of a vector point function a bar is equal to a1i plus a2j plus a through k is defined by del cross a. That is what we call vector product of del and a. We know a cross b, I have mentioned or defined already once, I have mentioned it in our presentation. A bar cross b bar is determinant of I is a k, dou by dou x, a1i, a1, b1, c1, a2, b2, c2. Similar you apply the definition here. Del cross a bar is I, j, k, dou by dou x, dou by dou y, dou by dou z, a1, a2, a3, and if we expand this, that's what we get. I into dou a3 by dou y minus dou a2 by dou z, so on and so forth. And irrotational, when one of the very important applications of curl is, if curl of any vector point function is 0, then that is called a irrotational vector, and that field is called irrotational. The word itself, irrotational, that means it is not rotating. It is not rotating. Rotation is not there. That is what we mean rotational. So when there is no rotation, what happens? The angular velocity. Rotation is connected with the angular velocity. If it is moving like this, it is called linear velocity, linear moment. If you are rotating like this, something like this, is something called angular moment or angular velocity is involved in it. Then when we say irrotation field, that means there is no rotational moment. Then angular velocity becomes 0, and the curl is a measure of the angular velocity at any point of the vector field. This is a very important application of curl in fluid mechanics, and in electromagnetic theory they find these applications of this curl and the irrotational concepts. If f bar is equal to xy square I plus 2x square yz z minus 3yz square k, find curl bar at the point 1, minus 1, 1. So curl f bar is given by del cross f I j k dou by dou x dou f by dou by dou y k dou by dou z of f1, that is xy square, f2 is 2x square yz, and f3 is minus 3yz square. So I into this dou by dou y at tyz square minus this thing minus j into dou by dou x of minus 3yz square dou by dou of xy square plus k into dou by dou x of 2x square yz minus dou by dou y of xy square. If you simplify this, we get this equation curl f, and at the point 1 minus 1 1, curl f at 1 minus 1 1 is given by minus I minus 2k. So find the constant ABC, excuse me, find the constant ABC so that the vector A is equal to x plus 2y plus az into I plus bx minus 3y minus z plus 4x plus cy plus 2zk is irrotational. Also find phi such that A bar is equal to grade phi. When you want to find this ABC here, given that A bar is irrotational, that means you have to find the curl A bar equal to 0 first. Then you will get the values of A, B, C. So A bar is so and so. Then curl A bar is I, J, K, dou by dou x, dou by dou y, dou by dou z, x plus 2y plus az, bx minus 3y minus z, 4x plus cy plus 2z equal to 0 bar. So I into this, j into this minus this, k into this minus this, what we get this. So I into c plus 1 plus j into a minus 4 plus k into b minus 2 is equal to, on the right hand side you have a 0 vector. So equate them to 0. So compare the coefficients of I, j, k on both sides. Coefficient of I is c plus 1, here is 0. So c plus 1 is 0 or c is equal to minus 1. Coefficient of j, a minus 4, 0. So a is 4. Coefficient of k, component along k is b minus 2, equal to 0. So b is equal to 2. So with this selection of a, b and c, this a bar will be irrotational. One more important theory we have here is, whenever a vector is irrotational, when a vector field is irrotational, we can always find a phi, a scalar potential called scalar potential phi, such that a bar is equal to grade phi. This is a standard result. Maybe I have missed somewhere I missed this result. It's an important, very important point here. Whenever, I repeat, whenever a given vector is irrotational, then we can always find a scalar function phi called scalar potential phi, such that this irrotational vector a bar is equal to gradient of phi. This is standard problem is whenever irrotational, you will ask to find scalar potential. So because a bar is equal to, now with a, b, c and b and c, after substituting, this is a bar. What is that? Find phi such that a is equal to grade phi. Now a is very well defined with a, b, c. So grade phi is I dou phi by dou x, j dou f by dou y plus k dou f phi by dou z. Okay, a is equal to grade phi. Now compare again quotient of I, j, k. So dou f by dou x becomes x plus 2y plus 4z. Now what is phi? Integrate with respect to x. So when this is a partial derivative, which is a function of x, y and z, then integration with respect to x means keeping y and z as constant. These things will be considered as constants. Then integral of x is x square by 2. Integral of this constant is 2xy. Integral of this is 4zx. Mind you, when we are dealing with y, x as variable and yz as constant, the integral constant in general may be treated as a function of y and z. Why? Throughout the process, we are treating y and z as constants here in this particular first equation. Okay. Now compare the quotient along j. Dou phi by dou y is equal to 2x minus 3y minus z. Now integrate with respect to y. When you integrate with respect to y, we assume that x and z are constants. Then integrate. So this will be constant. Integral of constant with respect to y is 2xy. Integral of 3y with respect to y minus 3y square by 2. Integral of this constant z with respect to y minus yz. Now the integration with respect to y. So the integral constant may be considered as a function of x and z here. I am sorry, this is x and z. Okay. Similarly, dou phi by dou z is 4x minus y plus 2z. Integrating with respect to z, assuming x and y are constants, the integral becomes 4xz minus yz plus z square. And because x and y are treated as constant, this constant is f3 of xy. So, if you see these things, commonly you can generalize this phi as x square by 2 minus 3y square by 2 plus z square, because in the first equation this is a constant f1 y. So you can check it. What is dou phi by dou x? Dou phi by dou x is 2x by 2 2x. Okay. So these things again, dou phi by dou x is 2 into x by 2, that is x. Here there is no x here. Here is 2y. And there is no x here. Here minus 4z. Should be actually 4z. Okay. So dou phi by dou y minus 3. Okay. Plus 2x minus z. Dou phi by dou z is, here we don't have any x terms. Here dou phi by dou z is 2z minus y minus 4z. So this is how we get a general expression. There is a mistake here. I have completed small positive and negative sign. That's why there is a change here and this thing I can correct it. Show that the vector field f bar is equal to 2xy square 2xy z square I plus x square z square so on and so forth is rotational. Find the potential function. These are the standard problems. So first, to show that it is irrotational, first find curl f ijk, dou by dou x, dou by dou y, dou by dou z, and this f1, f2, f3 here. Find this curl f. This is the vector. Clearly becomes 0. So irrotational. Then there is a phi such that grade phi is equal to f bar. I said no. Whenever a function is irrotational, a vector function is irrotational, we can always find a scalar potential function phi called scalar potential such that the irrotational vector f bar is equal to gradient of that. So gradient is dou phi by dou x I plus dou phi by dou y j plus dou phi by dou z k is equal to f bar. So as we did in the previous problem, compare the quotients of I bar, j bar and k bar. So dou phi by dou x is 2xy z square. Integrate with respect to x, this becomes x square y z square plus constant, a function of y and z, because integration is with respect to x. Dou phi by dou y is x square z square plus z cos yz. So integrate with respect to y. This is no y here. So it's a constant times y, x square z square y plus integral of cos y is sin yz by z plus integral constant is a function of x and z. Here dou phi by dou z is 2x square yz plus cos yz. So integrate with respect to z, x square y z square plus y sin yz by y plus u, the function of constant of x and y. So the most common function which satisfies all these three conditions is x square y z square. If you see dou phi by dou x, what is dou phi by dou phi by dou x here? 2x y z square. Okay. Dou phi by dou y is x square z square plus z into cos yz. Dou phi by dou z is 2x square yz plus cos yz into y. So this is the most common expression derived from these three equations. So this is your scalar potential. Now, under problem, phi satisfies Laplacian equation. Laplacian equation, this is also very important equation in fluid dynamics, thermodynamics, field equations. Del square phi is called Laplacian equation in 3 dimensions. If we elaborate this, dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0 is called Laplacian equation or Laplace equation. So this is called divergence of grade phi is equal to 0. That means grade phi is solenoidal. So the question may be, if phi satisfies Laplace equation, the following is true. Grade phi is irrotational. B. Grade phi is solenoidal. Grade phi is 0. Something like this. So your answer is grade phi is solenoidal function. Find A dot del phi at 1 minus 1 1 if A is so and so, phi is so and so. So you can go through the problem very easy, a simple problem. And gate 19 problem, we have phi of xy represents the velocity potential of a two-dimensional flow with velocity field u of xy I plus v of xy j in xy plane only. K is opposite. Which of the following is true? See, phi represents the velocity potential, scalar potential corresponding to velocity. So then v is equal to grade phi. When v is grade phi, then del phi is 0. That's what we have studied here. Laplace equation. Del cross v or del cross becomes 0. What is the curl of the vector field? This thing. Because I, j, k, dou by dou x, dou by dou y, dou by dou z, 2x square by 5z square. Very simple problem. Get 20. For a vector field A bar, which of the following is false? Del cross A is another vector field. A bar is irrotational if del square A bar is equal to 0. Okay. And del cross A bar is equal to del of del cross A. Just go through all the definitions once and check once what is the correct answer. See clearly which of the following is false. If A is a field, del cross A is also a vector and it defines another vector field. So A is correct. C. Del cross A is, we have standard vector identity. Del dot A minus del square is standard vector identity. And A is solenoidal if del dot A is 0. That is also true. Solenoidal, we call a vector as a solenoidal if del dot that vector is 0. That is also correct. We have some doubt about irrotational. If A is irrotational, del cross A is 0, but not del square A is equal to 0. And in fact, del square A is not correctly defined also. So the correct answer is B, which is a false statement. In gate 20, 2020, consider the following continuous differentiable function v of xy is equal to 3x square by I plus so on and so forth. The curl of the function. And things easily find out the curl of the function. For a velocity field given by v is equal to yi minus xj plus 0k, calculate the curl of v bar. The calculated vector is then values of a and b and c. Very easily you can do it. So some of the properties and vector identities we have then on depending on this del operated on vectors and scalars. Gradient of f plus or minus g, where f and g are scalar point functions. Whenever I say gradient, that means gradient of something, that something must be a scalar function. Whenever divergence and curl, that means divergence or curl of vector functions. Okay. So gradient of f plus or minus g is gradient of f plus or minus gradient of z. Divergence of a plus or minus b is equal to divergence of a plus or minus divergence of b. Curl of a plus or minus b is curl a plus or minus curl b. Gradient of fg is f into gradient g plus gradient f into g. The odd is not so serious here. And then del of f times a bar, f is a scalar. Then f into del dot a bar plus del f dot a bar. Then again f is a scalar function here. Del cross f a bar is f del cross a plus del f cross a. And divergence of a dot b is b dot del times a dot b times b plus b cross del cross a cross del cross. This is a very tough to remember, but it's a very important statement. You may have even questions directly on this. I think in some of the gate examinations, such inequality, some such identity was asked as a question with options. Del dot a cross b is b dot del cross a minus a dot del cross b. Del cross A cross B is triple product is also very important, and these 7 and 9 almost all you can derive one from the other. If you understand one thing, you can write the other thing. Next, so divergence of grade f, you have discussed this, is called del cross f, is called Laplace equation. We all discussed about this. Some more properties. Del dot del t is called del square f. Del cross del is always equal to 0 because del dot del cross f is 0. In a triple product ABC, if a vector is repeated, then obviously you need not verify, the product becomes 0. Triple product becomes 0. Del cross A, del of del dot A and del square A, del gradient of del dot A is so and so. These identity is very important. You have to remember there is no other option, there is no shortcut, and there is no so that any other trick. You have to remember, that's all. Then till now we have discussed the vector differentiation. Now we will go to vector integration. Integration of a vector function. Let f bar u be vector function such that df bar by du is equal to f bar u. Okay, then f bar u is the primitive of f bar u, small f bar u. So this is, you no need to work hard for this definition, leave it. Then properties of integration is alpha times f bar u is equal to alpha into integral of f bar u. Alpha is a constant. Then integral of alpha into f bar u plus r minus b into g bar u is, when a and b are constants, this is a into integral of f plus b plus r minus b into integral of z. This is called linear property. If f bar u is equal to f1 u I plus f2 u j plus f3 u k, then integral of f bar u du is equal to I into integral of f1 u du plus j integral f2 u plus k integral f3 u k. Definite integral is integral a to b f bar u. From this f bar u plus c between a and b, this becomes f bar b minus f bar a. The acceleration of a particle at any point at any time t greater than or equal to 0 is given by a bar t is equal to so and so forth. See, in differentiation the velocity is given and you are asked to find the acceleration, because derivative of the velocity gives you acceleration. In integration, acceleration is given to you, you are asked to find velocity. Don't get confused. One is acceleration from velocity, the other one is velocity from acceleration. If the velocity v and displacement r bar are 0 at t is equal to 0, find v bar and r bar at any time. So a bar is dv bar by dt is given by so. So to get the velocity you have to integrate this. So v bar is minus e power minus ti, integrate this, minus 6j t square by 2 plus t, and this is minus 3k cos tk, plus c bar is a constant, integration constant. Given that the velocity and displacement are 0, position vector are 0 at t is equal to 0. So put t is equal to 0 here. This is minus I. This is at t is equal to 0 completely becomes 0. Cos 0 is 1. So minus 3k plus c. So c bar is equal to, because this velocity is 0, this is equated to 0. So c bar is I plus 3k. So put this c bar here. Okay. If you put this c bar here, then v bar becomes minus this v bar plus c is I plus 3k. Take I common here, comes here. So v bar now is 1 minus e power minus t I minus 3t square plus 60j plus 3k into 1 minus cos t. This is v bar. And also r bar also. Then v bar is equal to dr by dt. I want the position vector also. Then integrate with respect to t. Integral of v bar t. So 1 minus the integral of this we get but t. Actually this is t plus e power minus t minus j into t cube plus 63t square plus 3k into t minus sin t plus c1 bar. At t is equal to 0, I think you get c1 bar is equal to minus I. Following the similar method, substitute there, we get r bar. This is a nice problem. Find the velocity and displacement of a particle having acceleration so and so at any time, given that acceleration and velocity are initially I minus j plus I plus j plus k. In the previous problem, velocity and displacements are 0. Then you are asked to find the velocity and displacement position vector. Here, given that acceleration and velocity are initially I minus j, I plus j plus k respectively, you are asked to find displacement and velocity. So, line integral. We have done now just general integration with respect to scalar variability. Now, you will be given a vector point function. You will be asked to integrate this along a curve T. Okay. So here what we have done is, in all these cases, we have integrated with respect to the velocity particle. We are integrating with respect to T. T is an interval. Okay. Integral 0 to 1, integral 0 to t. But here t does not have any direction, right? Now, the integration now is along a curve. The concept of definite integral into f of x dx, AB belongs to R, is extended to the integration along a curve. That means in a plane we have a curve like this, okay, and we integrate along this curve now. This is endpoints of the curve. Between these two endpoints, I have a curve like this, and now I want to integrate the given function along this curve. That is given by integral over c f of x y z dr. C is the given curve. C is said to be a closed curve or path. The standard terminology that we use in vector calculus, path. When the endpoints coincide. This is a curve like this. Okay. If both the endpoints coincide, this is a curve, open curve, like this. If this endpoint comes to the initial point, then it forms a loop or a closed path or closed curve. Then in that case, the integral is given by integral over closed C. Just we have a circle that represents a closed curve f of x, y, z. Let the parametric equation of the curve be r bar is equal to xti plus ytj plus zdk, where a less than or equal to t less than or equal to b, and f bar of r bar is f1i plus f2 plus f3k. The line integral of f bar r along c is given by line integral over c f dot dr. Just like in multiple integrals, we have line integral, double integral, triple integral. We have line integral, surface integral, and volume integrals in vector calculus. First, we are dealing with line integral. Integral of c f dot dr is fr is this one, dot r is xi plus yj plus zk. So dr is dxi plus dyj plus dzk. So integral over c f dot dr becomes f1 dx by dt, f2 dy by dt plus f3 dz by dt dt. So some points here, integral c k into f dot dr is, you can take this k out because k is a constant. Integral cf plus r minus g dr is f dot dr plus g dot dr, and c is a combination of two curves c1 and c2. Then integral over c f dot dr can be expressed as integral over c f1 dot dr plus integral over c2 f dot dr. These three properties, we will be using these three properties frequently. Then one important application of line integrals is force done by work done by force. We know that from physics, basic physics, if F is the force, F dot dr gives the work done. It's the simple same thing with from moving a particle from P1 to P2. If I apply a force F bar on a particle, say I have a particle here at P1, I apply some force here to move this particle from this place to this place. So F bar is given, P1 is given, P2 is given. Then what is the work done is F dot dr between the limits P1 and P2. That is work done by force. Similarly, in fluid dynamics also we use this idea of line integrals and we call it as circulation. If F bar denotes the velocity of a fluid and C is any closed curve in the field, then integral over C F dot dr is called circulation of F bar around C. Particularly, in general, I can talk about these things very superficially and go. But when mathematics is given to mechanical engineers, in the examination they may not ask you directly line integral. They may ask you find the circulation If F bar is a velocity of a fluid particle, find the circulation. Find the circulation means then you have to find the line integral over a closed curve C F dot dr. That is important. So, if integral over C F dot dr is 0, then the force F bar is called conservative. There is no work is done and energy is conserved. Why it is called conservative? Energy is conserved, so no work done is 0. So then F is called conservative field. In such case, F, just like in case of irrotational functions, here also we can find a phi such that F bar is equal to gradient phi. Then work done is independent of the path, and in case is del cross F bar is 0 and phi is called scalar potential. That means when is F is conservative field and this is initial point, this is end point, and the particle is moved from this point to this point by a force F. The force is and the field F bar is conservative, then line integral is independent of the path. Maybe between these 2 points you can have straight line, you can have curve like this, you can have curve like this, so many curves you can draw between these two, connecting these 2 points. But thing is, fact of the matter is, the line integral is independent of the path that is traced by the particle, like this, like this, like this. It is simply depends on the end points. This is a very, very, very important result, a consequence of conservative fields, property of conservative fields. The line integral, it simply depends on the end points, but not the path taken. So, it also means that conservative field implies international field. So F is equal to grade phi, then integral over P1 to P2, F dot dr is equal to phi of F2 minus phi of F1. It is in no way depends on the path. It depends on the endpoints P1 and P2 only. So F bar is equal to 3x phi I minus y square j. Evaluate integral over C F dot dr. Okay, where the curve C is y is equal to 2x square from 0 0 to 1 2. So here C is y is equal to x square or dy is equal to x dx, and F is given as 3x y I minus y square j. R bar we know that because we are in xy plane, z is absent, k is absent in F, so R bar is only xi plus yj. We don't consider z. So F dot dr becomes 3xy into dr is dx, 3xy dx, y square into dy. So this is what we get. Dr is dxi plus dyj. So along C, y is equal to x square. Okay. Or dy is 4x dx. So F dot dr is 3xy. Replace y, convert one of the variables into all the variables into one variable. So put this y is equal to 2x square, because why we have to do this is the integration is asked along this curve. Along this curve, y is equal to 2x square. We put that y here. So 3x into y, 2x square, minus y square is 2x square whole square dy. So F dot dr is, because everything is converted into x is changing from, in the problem it is 0 0 to 1 2. X is changing from 0 to 1. Y from 0 to 2. So what we need, because we have converted everything into terms of x, the limits of x are 0 to 1. So limits of x 0 to 1, F dot dr, so this is 6x cube dx minus 4x power 4 dy is 4x dx. If you include that, this is minus 8x power 5 dx. dy is 4x. So this comes out to be 6x power 4 by 4 minus 16 by 6 x power 6, between the limits 0 and 1 comes out to be minus 7 by 6. So this is under if ax and ay be unit vectors along x and y directions respectively, a vector function is given by f is equal to ax y minus ayx, where ax and unit vectors along x and y x. The line integral of the above function integral c f of dt along the curve C which follows the parabola. The curve is given by y is equal to x square. So given vector is ax is unit vector x axis by axis minus yx. integral C f dt need to calculate. C follows the parabola y is equal to x square. So what is dy? 2x dx. So f dot dr you have to calculate. F dot dr is y ax minus ay into x dot, here dot is missing, dot dx ax plus dy ay plus dz as. This is not there because we are only xy plane. This is not there. So y dx minus x dy. Okay, this is ax is unit vector. This is unit vector. So y dx minus x dy. But what is y? Y is equal to x square. What is dy? 2x. Substitute them here. Y is x square dx, and is x into dy is 2x dx. This is what we get, x square minus 2x square. This is minus x square dx. Then what are the limits of this? X is changing from minus 1 to 2. So put the limits, you get the value. Another problem is, if f bar is equal to 4x5 minus 3x square z square plus I bar 2x square j minus 2x cube zk, prove that integral over c f dot dr. You may not be in the examination. I'm telling you repeatedly, they will not ask you prove that, but they will ask you to evaluate this. Evaluate integral over c f dot dr. That means the work done. Directly they may ask you what is the work done here. We know that done is independent of the curve joining 2 points. So this happens only when curl f becomes 0. Okay. Question is this work done equal to 0 given f is equal to this thing, or is the work done depends only at the end points? This is the question, given that f is so and so. So for that you have to prove that f is curl f bar is equal to 0. Curl f bar becomes 0, then it is also called, we have discussed this idea already, conservative fields. So I, j, k, dou by dou x, dou by dou y, dou by dou z of this whole thing. So clearly curl f becomes 0. So this is a irrotational field or a conservative field. Then the work done is independent of the path. Question may not be like this. I repeat the structure. If f is so and so forth, can work be independent of the paths, or can the work depend on only the endpoints? The question can be asked in either way. Okay, be careful. The idea is that. Okay. So if f bar is a conservative field, it is given that conservative field given by f is equal to so and so, then the work done by f in moving a particle from 1 minus 1 to 2 to 3 to 2 minus 1 is. So it is a conservative field. You need not prove because it is already given. For information, I have solved the problem. How to show that a given function is a conservative vector point function. I had just illustration. I have done it, but it is given this problem that f is conservative. You need not do this part. Curl f is equal to 0. Just follow it. You will understand. Curl f bar is 0, so conservative field. So whenever f is conservative, we can always find a function such that f is equal to grade phi. So just like in the case of earlier problems, f is equal to grade phi. So I dou phi by dou x, j dou phi by dou y plus k dou phi by dou z. You compare with the coefficients of I, j, k, f in f and grade phi is equal to 2xy. Dou phi by dou y is equal to x square z cube. Dou phi by dou z 3x square y z square. So a common thing is, if you integrate this with respect to x, with respect to y, with respect to z, and the common function satisfies all these properties, is phi is x square y z cube plus constant. What is the result here? Whenever this f bar is a conservative field, then line integral of f dot dr does not depend on the path taken. It depends only at the endpoints and is given by integral p1 to p2 f dot dr is phi of p2 minus phi of p1, whereas phi is like this. So work done integral c F dot dr is phi of P2 minus phi of P1. So phi at 3, 2 minus 1 minus phi at 1 minus 1 to phi is this point. So if we substitute these 2 points in phi and subtract one from the other, we get minus 18 plus 8 is equal to minus 10. So we have a problem from gate 19. The vector function expressed by f is equal to so and so. See, the confusing part here is they are not using ijk here. In all the problems I observed that they are not using ijk. It is to confuse you. Okay, they are using in place of ijk they are using ax, ay, az. Don't get confused. Represent the conservative field where ax, ay, z are unit vectors x, y, z. The values of k1, k2, k3 are given by. So whenever this function is conservative field, what happens? What you have to show is curl f is equal to 0. So to find this k1, k2, k3, you have to find del cross f is equal to 0 equal to 0. Then this curl f is ax k3 minus 3 ay say 4 minus k1 and then k2 minus 5 equal to 0. So k3 is 3, k2 is equal to 5, k1 is equal to 4. And they are the constants and you have to pick the correct choice here. This is the problem given in gate 2009. So here if f bar is equal to 3xyi minus y square j, evaluate integral over c f dot dr where c is the curve, so on and so forth. Some curve is given, y is equal to curve is given as y is equal to 2x square from 0 0 to 1 2. Okay, the equation of the curve is y is equal to 2x square, so dy is 4x dx, so f is so and so. Since integration is performed in the xy plane, z is considered as 0, so f dot dr is, because r bar is dx I plus dyj, f dot dr is 3xy dx plus minus y square dy. But the curve is y is equal to x square and we have to integrate along c, so we have to substitute this y in this equation, in this integral. So y is equal to x square and dy, so this is what we get. So another problem here, a vector field is given by x by so and so, so and so, so and so, where ijk are unit vectors along x axis like a Cartesian system. The surface integral of f dot ds various. Okay, this is actually surface integral. This problem of surface integral, no need. We will do it in surface integral problems, not now, later stage. The line integral of vector function f bar r over a curve c in a simply connected domain D in space is given by integral over c f bar dot dr is f1 dx plus f2 dy plus f3 dz. The line integral is independent of path. You see, almost all the problems are focusing line integrals and conservative fields only. Logic is only basing on conservative fields and scalar point functions. Okay, the line integral is independent of path D means f is conservative. So f1, f2 and f3 are continuous and have continuous first partial derivatives, then c dash is closed curve in D. Which one of the following is not always true in D? Because the conservative field, this is true. Del cross f must be 0. And whenever this happens, f dot dr becomes 0. And it may be 0. Okay. Work done is 0. Because for conservative fields, no work is done. Energy is conserved. So work done is 0. This is correct. F cross f is always, we know that cross product a cross a is always 0. What is the only thing that is not correct is del dot f is 0. When del dot f is 0, this is called solenoidal, not irrotational or conservative. So answer is B. The value of the line integral is integral c f dot dr. It is asking gate 2018 where f is so and so, which is straight line from 0 0 to 1 1. I can do it. We have already done similar problems. Then coming to surface integral. So that means line integral means a curve in xy plane. Surface integral means a surface in the space. So see a surface such that it has a unique normal at each point. So there are some conditions on the surface here. We have to be very careful with that. So see a surface such that it has unique normal at each point. Then SC is called a smooth surface. Each surface at each point S must have only unique normal like this. That is called smooth surface. If SC is not smooth, then it can be divided. So means surface, some S is like this, and a joining of combination of two surfaces are there, then there may be a problem sometimes. Then S is not a smooth surface, then we can divide into finitely many smooth surfaces, and it is called piecewise smooth surface. So S is said to be oriented or two-sided if the positive normal direction at any point of S can be continued in a unique continuous way to the complete surface, and S must have two sides. Okay, these are the theoretical aspects. You can note down the point, that's enough. In no way related with our doing problems. Okay, consider continuous function f bar of R and surface S. The surface integral of f bar over S is defined by integral over S f dot ds or f dot n ds. So there are two representations here in the problems. Be very careful. The first here f dot ds bar. I said dot product. When do we define dot product? Dot product is defined only for two vectors. So f bar is a vector here. ds bar is also a vector. Area is it a vector? Yes. ds bar is called vector area, whose magnitude is equal to area ds bar, and which is the direction is normal to that point. Okay. So or else you can write this as f bar. N cap is unit vector, outward normal at P. Okay. Both the means same here, but I am using small s, means magnitude. Here capital S means vector. Observe the difference. ds bar is magnitude into unit normal. That's what we mean. Other types of the surface integrals are integral over S, f cross ds, or integral over S, f cross n cap ds. So one of the important application again fluid mechanics is flux across surface. It need not be fluids. This word flux is used in thermal conductivity. We use it in fluid dynamics, or we use in electromagnetic theory, or potentials or charges, charge flowing across a surface, that we call flux in electronics, and we use in electrical engineering also. If F represents velocity of a fluid particle, so I am saying it need not be velocity of a fluid, it may be charge, or it may be temperature, it may be anything, some velocity function. If it represents velocity of fluid particle, then the total outward flux of f bar across a closed surface is surface integral f dot n cap ds. Where flux across any closed surface in the region R is 0, f is called solenoidal vector point function. Okay. Evaluation. If f bar is equal to f1i plus f2j plus f3k, f1 and f2 are the continuous functions of x, y, z, then see, the surface is in the space, right? Like this is the x axis, y axis, z axis. The surface is like this. Very difficult to evaluate it directly. What we do is we consider is the projection in xy plane, or maybe yz plane, or maybe zx plane. Okay, and then we integrate. If we consider projection of S in xy plane, that is S1. So this is a three-dimensional body. If you consider the projection in xy plane, what happens? It becomes area in plane, xy plane. Okay, one dimension is neglected. Then it will be easy for us to evaluate the integral, because it's a region in plane. Using double integration you can solve, but that third dimension we have to take into consideration. How, we will see. So if S1 is the projection of the surface in xy plane, then integral over S f dot n cap ds is integral over S1 f dot n cap. The ds becomes dx dy by modulus of magnitude of n cap dot k. Similarly, surface integral becomes surface integral S2 f dot n cap dx dz by n dot j, provided S2 is the projection of the surface S in xz plane, and if S3 is the projection of S in yz plane, this is what happens. These three are very, very, very important. This slide is very, very important. If you want to do problems in surface integrals, Stokes theorems and other things, this slide is a very, very important thing. So evaluate f dot n ds, where f is xi plus F is Zi plus Xj minus 3y square Zk, and S is surface X square plus Y square plus is equal to 16, included in the first octant between Z is equal to 0 and Z is equal to 5. So the surface is surface X is this one. A, B, C, E, the circular surface, that's what we want. Okay. So F dot and ds, this is what we need. So n hat is normal to the surface. Okay. So grade phi is I dou phi by dou x, j dou phi by dou x, k dou phi by dou z. This is 2xi plus 2xi I plus 2yj. So n cap is 2 into xi plus yj by square root of x square plus y square. But the surface is the equation of the circle x square plus y square is 16. So root 16 is 4. So xi plus yj by 4. This is unit normal. So surface integral so surface integral now is taken projection yz plane. This is yz plane. dy dz by n dot I. So as I said the previous slide, f dot n is so and so. So this is how we do this problem. So f dot n ds is f dot n dy dz by n dot I. So that means xz plus xy by 4 into 4 by x dy dz. So put the limits, we get this. Evaluate surface area f dot n dot ds, where f is 18zi minus 12j plus 3yk and s is the part of the surface of 2x plus 3y plus 6z is equal to 12 in the first octant. So phi is 2x plus 3y plus 6z minus 12. That is the surface given to us. This one. So grade phi, to find the unit normal, you have to find grade phi. I dou phi by dou x, j dou phi by dou z, k dou phi by dou z, that is 2i plus 3j plus 6k. And unit vector along normal is 2ij plus 3j plus 6k by its magnitude, that is 4 plus 9 plus 36, 45 plus 14, 89, so 49. So the square root of that is 7. So let Rxy be the projection of the surface in the xy plane. So f dot n ds becomes double integral Rxy f dot n dx dy by n dot k. So 6 by 7 f dot n. F is this one, n is this one. So 18z into 2, 36z minus 36j plus 18y. So if you take common 6 by 7, 6j minus 6 plus 3y dx dy by n dot k. N is this one, dot k is 6 by 7. So if you cancel 6 by 7, this is what we get. So what happened? From the space 2, we reduce it to xy plane. In xy plane, what happens? By means of using z is equal to 12 minus 2x minus 3y by 6. By considering z is as a function of x and y, we have neglected one dimension, z dimension. So this becomes z is equal to, if you put z is equal to 12 minus 2x minus 3y by 6 here in this is what we have. Once you reduce it, we come to only xy plane. This plane 2x plus 3y plus 6z is equal to 12, 6z becomes 0. So 2x plus 3y is equal to 12. That is what is remaining for us. So y changes from 0 to 12 minus 2x by 3. And x changes from 0 to 6. I think I have not given a diagram for this. That is the problem. Okay. So now put the limits for this. X from 0 to 6, y from 0 to 12 minus 2x by 3 of this get 24. The surface integral f dot n ds, or the surface S of the sphere x square plus y square plus z is equal to 9, where f is equal to x plus yi plus x plus zj plus y plus zk and n is outward normal. You can calculate that using the given principles. So that comes to be. Then value of the integral r dot n ds, where r is, f is here, r is taken as f bar, or the closed surface S bounding a volume V, where r bar is xi plus yz plus zk is a position vector of n bar, the normal to the surface. Okay. So this is try it. That becomes 3 times V. R means xi plus yj plus zk plus R is, you have to find this n bar, and we have, using our usual methods of surface integrals, you can try it, comes out with 3V. And then coming to the volume integrals. Let V be a region in space enclosed by a surface R bar. Let f of R bar be vector point function. The triple integral is defined by triple integral V f of R dV. That means I into f1 dx dy dz, j triple integral f2 dx dy dz plus k triple integral f3 dx dy dz. So f is equal to so and so. Evaluate integral divergence of f bar. V is the closed region bounded by x is equal to 0, y is equal to 0, z is equal to 0, and the plane. We have considered problem like this. Okay, x axis, y axis, z axis. We have plane like this. Okay. Then what is the volume integral about this? The limits of z is equal to, from this z frames from 0 to 4 minus 2x minus 2y, and then neglect z axis. Once you consider the limits of z, forget about z, leave it. Then x dou f2 by dou y, that is dou f2 by dou y minus 2x dou f3 by dou z, that is 0. This is 2x dx dy dz. So because the limits of the first integral are in terms of x and y, that means they are the limits of z we discussed in multiple integrals. So we have to first integrate with respect to z. So 2x into integral dz is z between the limits. So the whole thing is now is a function of x and y, and the limits of y are in terms of x. So integration with respect to y first, then integrate with respect to y, substitute the limits of x. So the integral now is completely function of x, integrate between 0 to 2. This is what we get, minus 8. So basing on this line integral, Stokes theorem, surface integral and volume integral, we have 3 important theorems called Green's theorem, Stokes theorem, and Gauss divergence theorem. 3 important named theorems, very important theorems. What is Green's theorem? Let's say, first of all, Green's theorem is defined on a plane, not in a space. Plane means 2 dimensions, space means 3 dimensions. So Green's theorem in a plane, it's a relation between line integral and a double integral in a plane. R is a closed region in xy plane bounded by a surface closed curve C, and if m of xy and n of xy are continuous functions having continuous first order partial derivatives mx, my, nx and ny, then integral over C m dx plus n dy is equal to integral over R dou n by dou x minus dou n by dou y dx. This is called Green's theorem. How we apply for the problems is, find the circulation of f around the curve C where f is so and so. Circulation means integral over C f dot dr. Okay, f dot dr, where f is e power x sin y, I e power x cos y, dot dr means dxi plus dyj. So you get integral over C e power x sin y dx plus e power x cos y dy. What is Green's theorem? M dx plus n dy. So what is m here? E power x sin y. What is n here? E power x cos y. So integral over m dx plus n dy is equal to dou n by dou x minus dou m by dou y. So dou n by dou x minus dou m by dou y, dou m by dou y dx dy using Green's theorem. So dou n by dou x is e power x cos y minus dou m by dou y is e power x cos y. So circulation is 0. Find the circulation is 0. So you need not do anything. Integral itself is 0. Evaluate integral over C, close C, 2x square minus y square dx plus x square plus y square dy using Green's theorem, so on and so forth. Here m dx plus n dy is integral over C m dx plus n dy is equal to integral over R dou n by dou x minus dou m by dou y dx. This is Green's theorem. M is 2x square minus y square. See, here you have to write, when m dx plus n dy is given, f dot dr is, that means f is 2xi plus 2yj. That's what we call mi plus nj.